So in the last video we learned about the two power functions being even and odd and what their end behaviors did. And so in this video we want to talk about, well, if I know what is happening at the end of my graph, I have a lot of things going on in between those end behaviors. I have places where my function may cross or even touch the x-intercept. And we know these places. We've been able to solve for these particular values when we say want to find an x-intercept, when we've said in the past that we want to find the solution. We're going to add a word to that in case you aren't familiar with it already. We're going to also be able to say that I want to find the real zeros of my polynomial function. So anytime I am basically solving or finding the solution, or say that I want to find the real zero, what we are really finding are these places where we are either crossing or touching the x-axis. Now let's say we solved some polynomial, we found that it is going to cross, or we have an x-intercept at x is equal to 3. When we write that in its factored form, it takes this shape right here. In other words, if I know x is equal to 3, when I write it as x minus 3, that's what it looks like in its factored form. Notice that it's a positive 3 here for the solution, but it's minus 3 when we write it in its factored form. The way that we know how to do this, the way that we've been able to solve or find x-intercepts in the past with quadratic functions, is to either factor or do something like that. So that's kind of the idea for what we are doing. Now, let's just kind of back up for a second and see if we can create a polynomial function if we already know what the zeros of it are. In other words, this is where it's crossing or touching the x-axis. Can we go back and create the polynomial who would be something who would have these characteristics? So the first thing I want to look at is I know that this is a third degree polynomial, that these are the three zeros. So let's take these zeros and write them in their factored form. We have a negative 2, which when I write it in its factored form looks like x plus 2. I have a positive 2, which looks like x minus 2 in its factored form. And I have a 3, which looks like x minus 3 in its factored form. Notice that the root and its factored form have opposite signs. Now to form the polynomial, we take all three of these factors and we just multiply them together. So I have x plus 2, x minus 2, x minus 3. I could take each of these three factors, set them equal to 0, and solve to get my roots if I wanted to go backwards again. But I want to actually simplify or expand, get rid of the parentheses here, to find the polynomial. To do that, I'm going to just kind of handle these in pairs. So I'm first going to multiply x plus 2 times x minus 2. Using FOIL, I can multiply these two numbers together, or these two binomials together, and I get x squared is the first term, minus 2x for the outer, plus 2x for the inner, gives me a minus 4 for the last term right there. Now that I have simplified these two binomials, I'm going to multiply times the third. So again, I'm kind of doing this in pairs. And I'm just going to use the FOIL again in this last step. So I get x squared times x is x cubed. The last is negative 3x squared. The inner term is negative 4x. And the last is positive 12. And it just so happened that this all fell into descending order rather nicely for me there. But this is the polynomial function, who is a third degree polynomial with zeros at negative 2, 2, and 3. Now, let's try one more example where we want to look at it a little bit differently. Here is the polynomial that I have, and I want to go backwards. I want to find the roots of this polynomial. Remember that if my polynomial is already factored, to find the roots, all we need to do is set it equal to 0 and solve for x. That allows us to use what we call the zero product rule, which means I can, if this whole function is set equal to 0, then I can set each of the factors equal to 0. So when we look at this, we see here that we have 3 times x plus 1, x minus 3 quantity squared, x minus 1/2 cubed. And all of that is set equal to 0. Well, if I take each of these 4 factors and set them equal to 0, the 3 is just going to cancel off, leaving me with x plus 1 equals 0, x minus 3 squared, x minus 3 squared equals 0, and x minus 1/2 cubed equals 0. So just looking at each of these 3 simple equations, starting with the one over here on the left, move 1 to the right hand side, and we find out x is equal to -1. This second equation, in order to solve this, I can use the square root property, which says I can take the square root, since I'm squaring this. When I take the square root of both sides, it just gives me what was inside of those sets of parentheses. X minus 3 equals 0. Therefore, x is equal to positive 3. And we can apply the same principle over here. If I am cubing a function, then I can take the cubed root of both sides, which simply gives me what's inside of that innermost set of parentheses, and I find out that x is equal to a positive 1/2. So what I found then is that I have roots occurring in this function at -1, positive 3, and positive 1/2.